So can't get around the question from the review worksheet with you. I'll let my little slide here. Today, we're going to start solving equations in exponential form. And I think that you'll find these pretty straightforward. On Monday, we're going to solve logarithmic equations. So I split it up into 2 separate days. So today we'll focus on solving equations in exponential form. Monday, we'll look at equations that involve the log function. And then Tuesday, we'll kind of summarize section 7.6. Wednesday, we'll review. And then, as I said, next Thursday is the non-calculator portion. And Friday is the shorter 2-problem calculator portion. One problem's a little larger than the other. But we'll talk more about that next Tuesday and Wednesday. So homework tonight is in the book. Monday, it's also in the book. Julia. Will either of the tests? You know what? My hope is yes, but I don't know. I probably could put Thursdays on, but Fridays, I don't know. They kind of go together though. So I feel like I'm going to do an all or nothing deal. I have to think about it. That's kind of cutting it close. We'll see. We can take a vote next week too, see what everybody wants. It will be on paper, so they will be paper tests. Right now, I can't grade anything on Google Classroom on the iPad. I have to like type all the comments in, which isn't really math friendly. Trying to type in exponents and all that stuff just doesn't work very well. So. Oh, I have them. They're good. I'll give them back to you then. Thanks for reminding me. I have them right here. They were good. I'll give those back. All right, so let's look at the last graphing problem of the worksheet from yesterday. 9a and b were both log functions with a base of 3. So you could have used the same t-chart for A and then that t-chart for B because the base was 3 in both cases. So let's just kind of think about that. When you're graphing a log function, it says to make sure you have 2 t-charts because really you need to think about the exponential function. And the exponential function, the base is 3, so that creates our exponential function. So make a little t-chart here. And then we'll pick some x values. So when I plug in negative exponents, we know that makes a fraction. A 0 as an exponent always is the value 1. 1 is the number itself, and then 2 squared becomes 9. All right, so to find the log function, Gabby Snyder, what do you do if I'm trying to find a log function using the exponential form? Yeah, so you switch the x and y. So I'm going to switch the x and y's. And now I have a 9, 1/3, 1, 3, and 9. And then we still have -2, -1, 0, 1, 2. All right, so before we go and graph this, I want to talk about the equation that we're dealing with. We are looking at f of x equals negative log base 3 of x and then -1. There's 2 things in this problem that I want to kind of note. Let's talk about the -1 first. What does that -1 do to every point on the graph? Brooke? Close. So the x is where our h value is, and the k is the number outside. And if there's not parentheses grouping x and the number together, like there are in EA, so look at A versus B. So A has parentheses with that x plus 2. But B, the -1 is by itself. It's not in parentheses with X. So Gabby Soul, what does that mean that -1 is really doing?
Move it down.
It's going to move it down 1. So that's kind of tricky to think about. So anytime it's in parentheses, it's affecting X. If there are not parentheses, then that -1 or +2 or whatever number it is affecting Y or moving it up or down. So this graph is going to go down 1. So it's supposed to be in parentheses X minus H, and then the K is always separate from X.
So how would the X plus 2 affect the translate on that one?
So this is really X minus a -2.
So I'll move it to the left.
So this one moves left too. Good question to ask. All right, so we know this graph is going to move down 1. We're going to do that part in a minute. But there's also a minus sign in front of the graph or in front of the log. That minus sign is saying you're supposed to take your log and make it negative. Well, the function is the y. So in your t-chart, we need to make all of those y values negative. So I'm going to do that before I graph. So there's the negative in front of the log. That means all of my y values, because that's the function is y, f of x and y are the same thing. All my y values need to become negative. So if it is negative, that means it becomes positive. So this is a +2, a +1, 0, and now a -1 and a -2. All right, so I'm going to graph this t-chart. Remember, we are not graphing the exponential, we're graphing the log. So I'm going over to 1/9 and going up to 2. At 1/3, we're up at 1. And then we have a point at 1, 0, 3, -1, 9, -2. Remember, these have vertical asymptotes. The graph should skim next to the y-axis. So that is my original graph. Notice that it goes down because of the negative in front. And that happens with the parabola too. So when we had x squared, it was up. When we had -x squared, it went down. A negative makes the graph go down. The last thing that we have to do is now move the graph physically down 1. So Gabby said that -1 moves each point down 1. So I'm going to go to each point and move it down 1. Our graphs end up overlapping at the vertical part of it because the only thing that's happening is the graph is just shifted down. But vertically, it's still skimming along the y-axis. And that's where your asymptote is located. So make sure you include that in both A and B. Make sure you have that vertical asymptote. If it's not shifting left and right, then it's on the y-axis. If it shifts to the left, then it's wherever that shift is. How far did it shift to the left? Questions on that graph? So the domain would be starting at 0 because it's not going to the left any further than the y-axis, so it has to start at 0. The range is always -infinity to +infinity because it stretches up and it'll gradually continue to curve down as it moves further to the right. So again, we first found the base and we made it an exponential function. So the base was 3. We found a t-chart for the exponential function. We switched to the x and the y because that's how you get the log equation, the log graph. And then because there was a negative in front, we took all those y values and we made them opposite. So a negative function or a negative in front of your function makes it go down instead of it going up. Questions? Yeah, Brooke.
I have a question on this one.
Yeah. Sure. Yeah. For letter C, you said, right? Yeah. Okay. So we have the log of 64. Division can really be separated into subtraction. Okay, so let's do that. We're trying to use the log of 4 and the log of 7. So that means 49 could be changed to. Yeah, I knew what you meant, 7 squared. And then that little 2 can move in front and become 2. And then the log of 7. How could you rewrite 64 as an exponent? Exactly. And then the 3 comes in front, and we have then the log of 4. So I would take 3 times 0.602 minus 2 times 0.845. Julia. 4, you said F, right? Okay. Any questions on C? Here, I'll zoom in, Malachi. Okay, so if we look at letter or number 4, yeah, so 4F says express as a single logarithm, and it says show all work, which should be pretty standard at this point. Math is about the process, not always the answer, but how you arrive at that answer. So looking at 4F, single logarithm means condensed. So we want to pull these together. In order to pull them together, we need to look at the problem and see what's going on. First thing I notice is this 4. That becomes the exponent. So we have the log base 5 of 25. And then we have the log base 5, and it's the square root of 5. How else could you write a square root? Ella? An exponent of 1/2. So I'm going to write this 5 with the exponent of 1/2. But then that 4 is with that 5 to the 1/2 because it's really the square root of 5 to the 4th power. Well, the square root is 5 to the 1/2, and then that's to the 4th power. So Ella, what happens if you have 5 to the 1/2 and then outside the power of 4? Because what do you do with exponents? You multiply them. So that becomes 5 squared. All right, so now I have the log base 5 of 25 minus the log base 5 of 25. What do you notice about these two things, Ella? They're the same. So if x minus x is 0, 27 minus 27 is 0, xyz minus xyz is 0. The log base 5 of 25 minus the log base 25 base 5 of 25 is 0. Yeah, it is a regular subtraction problem. Oh, you switched them to be bases. Yeah, that's fine. questions? Yeah.
I just kept it as I kept this.
Oh, you actually, yes. Yep, that's fine. That is, yep. So you made the 5 to the 4th and then you took the square root. That's fine. Yep. All right. So as I said, today we are going to look at solving some equations. In your packet, if you will turn to section or slide, scroll's the right word, right? Scroll to section 7.6. And we're going to start the last section of our packet. The last section of our logs and exponents chapter. And as I said, I think you'll find that this exponent form is pretty straightforward. We just have to remember some of those properties of exponents. So solve exponential and logarithmic equations. First, we're going to start off with a refresher of those two forms. So exponential form is y equals e to the x. That's our exponential form. Jaden, how would you write that in log form? Yeah. So remember, the exponent and the y switch. So instead of it equaling y, it's now equal to x. So y equals b to the x, log base b of y equals x. When we solve exponential functions, we may need to make it a log function in order to solve it. That's why logs are created, to help us solve exponential functions. We're going to use that property when we get to the second group of problems. The first group of problems use the property of equality for exponential equations. Equality means equal. So it says if b is a positive number other than 1, then b to the x equals b to the y. So this base has to be the same. So 2 to the x equals 2 to the y. 7 to the x equals 7 to the y. And then it says if and only if, and that's that conditional statement from geometry. If and only if x is equal to y. So if my bases are the same, in order for these exponents to have the same value, the exponents must be the same or the powers must be the same as well. So little example here, if 5 to the x equals 5 to the 4th, then x has to equal 4. Because if it doesn't, then 5 to a different power is not equal to 5 to the 4th. If x equals 4, then 5 to the x is equal to 5 to the 4th. That's how a conditional statement works. I can work through it one way, and I can work through it the exact opposite way, and it holds true. So we're going to work on this conditional statement and this property to help us solve the first group of problems. Solve the following by equating exponents. We're going to try and make the exponents the same. But in order to do that, our bases need to be the same as well. Right now, we have 64 to the x equals 16 to the x plus 4. How do you think you would start this problem? Our bases aren't the same. They have to be the same for this to work. Gabby? Yeah, so we're going to break them down into the same base. So write it as an exponent. So Gabby, 64 is 4. Yeah, to the 3. And then that x was already there. So we're going to just place that x next to it because you're multiplying them. And Gabby, 16 is really 4 squared. And then I'm going to put that x plus 1. That's a quantity. Anytime it's a quantity, you have to think that there are grouping symbols, parentheses around that quantity. All right, the bases are the same. So this is saying if the bases are the same, then I can solve for the exponents so that I can take 3x and set it equal to 2 times the quantity x plus 1. So we're going to solve for the x in the exponents. So 3x equals, I distribute that 2 through, I get 2x plus 2. That's where my x is located. I want to find x so I can set the exponents equal based off of equality. And then when you take the x to the other side, you end up with x equals 2. And that's it. So make the bases the same, solve for the exponents. But when there's a quantity, that 2 distributes to both of those quantity values. So let's try the next one. We have 4 to the x equals 1/2 to the x minus 2, or x minus 3, I'm sorry, no, x minus 2. We need to make the bases the same. So, Julia, how could I change the 4? Let's start with that. How could we change 4? So we're not going to divide by 2, but I want you to write 4 as an exponent. So how could I write 4? 2 squared. So let's change 4 to be 2 squared. How could I change that 1/2 so that it is a base of 2? So think 1/2. How could I write it as a base of 2, Faith? 2 to the negative 1. Remember, a fraction is really a whole number with a negative exponent. So 1/2 is really 2 to the negative 1. And then we have that x minus 3. So the bases are the same. Now you're just setting the exponents equal. So 2x is equal to, make sure you distribute the negative 1 through, negative x plus 3. Which means 3x is equal to 3, so x is equal to 1. Questions? Why don't you try the next pair? 9 to the 2x is equal to 27 to the x minus 1. Try the second one as well. 81 to the 3x minus 3 minus x equals 1/3, and then to the 5x minus 6. Remember, when you're solving for x, you can always check your work. You can mentally plug that in and make sure that those exponents are remaining the same. Once you have that same base. So 9 we know is 3 squared, but there's a 2x there, so that makes 4x. On the other side, 27 is 3 cubed with the x minus 1, which makes it 3x minus 1. So Alyssa, x would be equal to, in part C. -1, yeah. And then looking at part D, Riley, how could you change 81? Yeah. And then how'd you change 1/3? Yes. Ella, question? Oh, I didn't distribute that 3. I was going too fast. That's why Alyssa was like, what the heck? Thanks. So then it's -3. Sorry, Alyssa. I was moving too fast. Thanks, Ella. All right, so then Riley, what do you have in your next step? Yep. And if we add the x to the left and take the 12 to the right, we end up with x equals -6.
Even because I got -1 too, and I'm trying to.
Well, you may have not, maybe you didn't distribute like I didn't distribute.
Yeah, I cubed 3 instead of squared it.
No, yeah, that might be too. Yep. Yep. Any questions with this property of equality for exponents? Let me zoom back in here. All right, so that's one way to have exponential equations, when I have an exponent equal to an exponent. But that's not the only type of equation that I can solve, because I might not have an exponent equal to an exponent. We might just have an exponent equal to a number on the other side that can't be written in exponential form. So the next group of problems that we're going to solve are going to involve that conversion fact, the exponential form and the logarithmic form. So those are going to be the next group of problems that we look at. Questions with solving for exponents with getting the base the same, setting the exponents equal. So in the next group of problems, it says solve the following by taking a logarithm. And then it says of each side. We're really going to be changing it to logarithmic form. So if you look at 6 to the x equals 27, is there a power of x that'll give us 27 when we're talking about 6? Well, 6 to the first is just 6. 6 squared is 36. So that means 6 to the x has to be between 1 and 2. But we don't know what number that is. So in order to find that value, we are going to change this to log form. So logs were created so that we can solve for exponents that aren't exact values. And we can't change 6 and make it like 2 squared or 3 squared because it doesn't have a perfect square. So Grace, how would you write 6 to the x equals 27 as a log? Yeah. So now, this is the part that would be on the other form of the test. You have to use your calculator. So this equation wouldn't be on there if you have to use your calculator. It's going to be on the calculator portion. In your calculator, you can either take the log of 27 and divide it by the log of 6, or you can use that change base form. Go to math, hit the log base, and we have the log base 6 of 27. There's no way around not using the calculator in this problem. So again, log of 27 over the log of 6, that's what the calculator is really doing. Or you can use the calculator's function, enter it into your calculator, and you get 1.839. We'll keep 3 decimal places there. So x is approximately 1.839. So if you can't do anything with it, then you have to change it to log form. There's nothing to do with the exponent. Let's look at letter B. So thinking about solving equations, comparing A to B. Notice A, the exponent is by itself. So what do you think you would have to do with letter B? Knowing what you know about solving equations. So think about what you know at this point. Ella, what do you think you have to do? Yeah, right, to get the 8 to the other side, because we have a like term with an 8 and a 20, they're both numbers. So 6e.25x equals 12. Ella, what else do you think you'd have to do? Divide by 6. So e to the 0.25x equals 2. We just isolated the exponent. So here's our exponent. We need to isolate that. It needs to be by itself. Just like when we had radicals, they needed to be isolated. That's a key thing of solving for x. You've got to isolate the variable. So now we have e to the 0.25x equals 2. It's isolated. There's nothing else we can do with it in exponential form. Ella, how would you change this to logarithmic form when the base is e? So what goes along with the base e? Yeah, so we're going to take ln. Technically, the base is e. You don't have to write it. It's implied. And then you're taking the natural log of what number, Ella? And it's equal to 0.25x. Now, before you put this in your calculator, because I don't want you to round 15 times, or 2 times, or 3 times, we're still going to get x by itself yet, because there's 0.25 still attached to x. So in order to get x by itself, we have to divide by 0.25. In your calculator, you're going to type in the natural log of 2 divided by 0.25, all in one step. So natural log is on the left next to 4, and then divided by 0.25. Make sure that parenthesis closes after the 2. And I have 2.773 if I'm rounding up. Questions with solving that? All right, so we got 2 more problems here. And C and D look very similar to A and B. So for B and D, I need to isolate. For A and C, the exponent was already by itself. So Brooke, how could you take 5 to the x equals 72 and write it as a log? And then Brooke, when you plug that in your calculator, you get 2.657. So if the exponent is by itself, the only thing you can do is write it in the other form, the logarithmic form. For letter D, this one we need to solve. So Gabby Snyder, first we would take 7 to the other side. And then, yeah. And finally, yeah, write it in the logarithmic form. Anytime it's an E, you use the natural log. So the natural log of 5 equals negative 0.3x. And then just make sure you're dividing the natural log of 5 by negative 0.3 to get x by itself. Negative 5.365. Yeah. Mrs. Kane. Hi, good, how are you? That's all right. Yes, I can. Bye. All right, so homework 3 to 23 is the group of problems from your book. The first group are like the equality. The second group are getting the logs by itself and are getting the exponent by itself. I can point you in the right direction. Anybody have questions? All right. Have a